have Maryam, who talked about leveraging predictions for efficient hypothesis testing of discrete distributions.
Thank you. So going to talk about leveraging prediction for hypothesis testing. So we live in an era that we collect and produce a lot of digital data, and an important task is to essentially extract meaningful information from this vast amount of data. Statistical inference essentially is the theoretical backbone of this fundamental question. We have a population. We assume that there is an unknown distribution over this population. We view our data set as a set of random examples or random samples from this underlying distribution, and we want to design an algorithm that extracts meaningful information from the underlying distribution. There are a variety of tasks that we can consider here: hypothesis testing, parameter estimation, classification, and all sorts of learning tasks under this general framework. The main goal is data efficiency, so I want to use as few samples as possible to do this task. You can think of other notions of efficiency, but for now we're just thinking about the data efficiency. So the main assumption here is that we have IID samples from an unknown distribution, and the distribution is unknown, but there are many cases that the underlying distribution is not entirely unknown. And we might receive some prediction or advice about this underlying distribution. So this talk is about incorporating that advice into data analysis. So let me give you a few practical examples that you might have some information about the underlying distribution. You might actually collect data in various places and over various times, so the data that you previously collected might be helpful, or the data, for example, the search engine queries that you have in a country could help you to figure out the search engine queries in another country. Sometimes there are heuristic rules that can help you essentially estimate or come up with some prediction about the underlying distribution, or it could be an ML model, especially that they're so common these days that it might actually give you a prediction. So now we are studying this setup, and in addition to the samples from the true distribution, you're receiving some sort of advice distribution as well. So what is important here is that you might have some true distribution, but the quality of advice is not actually predetermined before. So you might have different sort of prediction, and it could come in variety of the quality, and you still want your algorithm to be able to exploit as much as possible from the advice. So the behavior of the algorithm that I'm looking for is an algorithm that has an adaptive behavior to the quality. As the quality of the prediction degrades, the sample complexity would go up. Hopefully, I'm never going to go above the worst case that we would have in the standard setting. So for those of you who are familiar with the setup of distribution with prediction, there are two things that they care about: robustness and consistencies. Like robustness says that you would never go beyond the worst case possible thing that you would be in the standard setting when there is no advice. And also when the prediction is good, you get the right behavior and you see this drop. What we want is essentially the whole curve, so adaptive behavior. So I think the first time that you probably see this problem, the first thing that comes to mind is that, is this even always possible? So the answer is no, and especially for estimation tasks, it's much harder to use any prediction, even when the prediction is correct. So if you have a coin, and someone tells you, I promise you that this is an unbiased coin, you still need 1 over epsilon squared sample to essentially figure out whether the bias of the coin is 0 or it's like epsilon biased. So in certain tasks, the prediction is not helpful, but hopefully we can focus on problems that there are some underlying the structural information in the prediction that we can exploit, and they're easy to verify. So I can verify those structural properties with fewer samples than I would need for the standard task. There are some prior work on the distribution testing setting. Most of these works, they have access to the underlying distribution in an approximate way. For example, I can query a probability, the probability of an element up to a constant factor or 1 plus epsilon approximation. But all of these works, they mainly focus on the case where the prediction is promised to be correct. Within the 1 plus approximation, the distribution seems to be correct. What we do is essentially want to remove this the correctness assumption of the prediction. So we assume that the algorithm received a description of the distribution. So here, assume that the advice is a known distribution. And we also assume that we are given a parameter alpha, which I'm going to talk about later, but think of alpha as a promised accuracy level, so or like error level. When alpha is 0, we have perfect prediction. When alpha is larger, we have sort of bad prediction. But the alpha is not guaranteed, it's just suggested. And then the algorithm has two options. It can either solve the problem, or it can refuse to solve the problem and say no, but under this sort of condition that when the prediction is not alpha close to p, then the algorithm gets a chance to essentially not solve the problem. So in this specific model, I assume that p hat is free. I'm not going to pay any sort of sample complexity cost for p hat. You can assume other access models to p hat as well. But for now, let's assume our goal is to only minimize this m, which is the sample complexity of the algorithm, from the true distribution. So the error guarantee of this algorithm is kind of similar to what you would expect in the standard case. You want the probability of outputting the wrong answer to be low, but you also want the algorithm actually solves the problem when the prediction is good. So if the prediction is good, the algorithm is not allowed to refuse solving the problem. So what does this mean? It means that the algorithm, when the prediction is wrong, the algorithm essentially gets a pass. It can say, I don't want to solve the problem. But if the algorithm decides to solve the problem, the answer must be correct. This is sort of a good resilience in the behavior of the algorithm that we can exploit to have that adaptive behavior that I talked earlier. In particular, if your algorithm has this behavior, you can essentially search for the right value of alpha. I can start with a very small alpha and gradually increase alpha up to a point that my alpha passes the right threshold of the alpha, the true quality of the prediction, and at that point my algorithm definitely answered the question. If my algorithm answered the question before we pass this threshold, still it's going to be a correct answer. So regardless of when I stop, I'm going to output something correct. And this whole search behavior does not blow up the sample complexity by more than polylog log factor. So we're good. As long as the algorithm has polynomial sample complexity. So let's focus on our main problem, which we will see different versions of it. So we consider the closeness testing problem. This is a very fundamental problem in distribution testing. We have two distributions, P and Q. We receive samples from these two distributions. And in the standard setting, we want to accept if P is equal to Q, and we want to reject if P is far from Q. In here, I define farness in an L1 norm, and L1 distance. So if the L1 distance, which is the absolute differences of the probabilities, if that distance is larger than epsilon, I want the algorithm to reject with high probability. So let's think about an example. Let's say I want to test whether a particular treatment affects the blood sugar. I have two distributions, the blood sugar level for patients who receive placebo and the standard blood sugar level for the patient that receives the treatment. Ideally, if blood sugar is not a side effect for that, increased blood sugar is not a side effect for that particular treatment, I should see the same distribution, and otherwise I will see different distribution. But a particular example that would be interesting is that if I want to solve this problem for a particular subgroup, let's say a group of cancer patients, then I want to still solve the problem for that small group, but I potentially have a lot fewer samples from those patients. So now the question is, does the samples from the general population, the patients that the non-cancer patients, would help me to do this task faster and in a more efficient manner. So if we study this problem in the augmented setting, we receive, in addition to the samples from P and Q, we receive this p-hat and alpha, and we also get a chance to say null if the prediction is wrong. So the result that we have is that for closeness testing problem, the sample complexity reduces with the value of alpha. So if we have, so the black terms are essentially what you need in the standard setting, and it's optimal. And what we could do is like get this factor of alpha to the 1/3. So if you have a distribution that is close, you get an improvement in the sample complexity. We have matching lower bounds, and the lower bounds are sort of information theoretic. So even when the prediction is true and the true alpha is given to the algorithm, the problem still requires the same number of samples. Another result that we have is for uniformity and identity testing. These are essentially the same problem as closeness testing. The only difference is that Q is for the uniformity testing, Q is the uniform distribution, and for the identity testing, Q is another known distribution. So instead of samples from Q, we have the description of the Q. And in this case, this is the sample complexity that we are getting. So an important twist about these two problems is that very similar to the first lower bound that I showed you for the coin problem. In this problem, you need at least the square root 10 over epsilon squared samples to figure out what is your underlying distribution. Even if the prediction is really good, you still need to check that, and it's essentially not very possible to go beyond what you could normally do. And this term that is here, just a quick explanation, in the case of farness, the prediction can tell you exactly where to look for an evidence of farness, and that's how the prediction is helping you and drastically could potentially reduce sample complexity. However, this is not always the case. Like, for example, if the prediction is correct, you would not be able to use such witnesses, essentially. Another problem that we studied is independence testing. So you have a distribution over a pair of random variable xy, and you want to see if xy, x and y are independent or they are correlated. This is equivalent to check whether a two-dimensional distribution P is equal to the product of its marginal. So this is another version of closeness testing if you think about it. And this is the sample complexity that we got. And the black terms are essentially necessary for the standard setting. We also study the same problem in the context of differential privacy. What we have for the model is that this is the same as the augmented testing, but we want to protect the sample. So P is still considered as something publicly available to everyone, so we don't care about the privacy of P hat, but we care about the privacy of the individuals who participated in the data set. So I'm not going to define the privacy, but general standard DP, central DP definition says if we change one sample in the data set, the behavior of the algorithm should remain almost identical. So there are a lot of work in the domain of differential privacy that they start training on public samples, and then they use private data to sort of fine tune. So this is, in a way, has some similar flavor. Here we assume the public sample, we had a lot of public samples, so we learn the model with the public sample as much as we want, and then we sort of do the private part to make it closer to what we want. These are some theoretical work. Again, some of them assume the quality of the prediction is fixed and given. And this last one is kind of similar to ours. That it has the adaptive behavior. The difference is that they're looking for the not the distributional case, but the data, what is it called? The percentile of the data set and not the underlying distribution. So these are some previous work. So let me give you a little bit of So this is our result for the private closeness testing. As you see, there are all sorts of terms in here. These terms are essentially the terms that caused by privacy, and the C is our privacy parameter. And we can show all of these terms are optimal up to logarithmic factor. So what you can see is that both in the closeness testing problem and this problem, as the quality of the prediction gets better and better, your sample complexity somehow interpolates between the closeness testing and the uniformity testing, or known Q essentially, or identity testing. So it's like when you get good prediction, your sample complexity becomes similar to the problem that the underlying distribution, one of the underlying distribution is known, which is nice interpretation. And this is something that we would expect because P hat is essentially that distribution. So let me give a very short explanation of our technique that you might find it interesting. So I'm going to talk about this term, how we got this alpha to the 1/3 in the closeness testing problem. I'm just going to talk about the upper bound. Okay, so let's start with a known closeness tester. This is actually an algorithm for introduced by Elias and co-authors. This is an algorithm for estimating the L2 squared distance of two underlying distributions. And the sample complexity of this particular statistic is n over epsilon squared times the L2 norm, the maximum L2 norm of the two underlying distributions. And this is very interesting because the L2 norm is a number somewhere between 1 over square root 10 and 1. Right? So this is variable depending on the structure of the underlying problem. And if you compute the sample complexity, you would get something like a square root 10 over epsilon squared, or you could get n to the epsilon squared. So this is like the best thing that you can kind of hope for. This is almost the lower bound on every distribution testing problem and discrete distribution. And this is the place that you can almost learn the distribution. So at this point, you can solve any problem because this is so many samples. And below this term, you cannot really hope to do anything. So this sample complexity can essentially be anywhere in this range, which is really nice for us. This flexibility to the underlying structure is something that we are going to do. The true standard sample complexity of the optimal algorithm is somewhere here, but as you can see, we can actually have a chance of achieving something lower than the optimal for the closeness testing, and this is So what I want you to remember from this slide is that if I reduce the L2 norm, I would be able to get a more efficient tester. Okay, so how does the standard optimal closeness testing algorithm work? It takes a distribution and it tries to reduce its L2. What is L2 norm, or L2 norm squared, is the sum of the probabilities squared. If I can show that there is no too large probability elements, then I can show that the L2 norm is small. So what we're gonna do is that we identify the large elements and we're gonna split them into smaller pieces. So here, let's say I have this purple element. I'm gonna divide its probability into 3 pieces and then put 3 elements back into the distribution with the probability pi divided by 3. So the main difficulty, or like the main challenge that we have to do in here is that to figure out how many bins I should assign to each probability. And if I have that if I have the number of bins, I can pretty much do anything that I want to do to the original distribution. I can do it on the flattened distribution. So I can sample the underlying distribution, and it also preserves the L2 norm between the distributions. So if 2 distributions used to be equal, they will remain equal, and if they used to be far, they will remain far. So this gives us a structure of the optimal algorithm. We can draw samples from the original distribution, we flatten them, and then we test the equality of the flattened distribution. Because these flattened distribution, they have a lower L2 norm, we get the optimal sample complexity. So here I'm going to talk about how we can flatten using the prediction so we can actually make this even better.
Okay, so in the standard setting, we don't have any access to the distribution except the sample. So when we sample from the distribution, if we have a high probability element, we will view it further. Like we will observe it more in the sample set, and this allows us to essentially flatten the distribution. So the higher the element is, the more it will show up in the sample set. And I can check the frequency of element I to inform me about the binning. If the frequency is high, I'm going to put more bins. In the prediction case, in our case, what we do is that we still use the frequency of the element in the sample set as an indication for how large the number of bins should be. But again, I can use prediction to inform me about the number of beans as well. So I pick the number of beans to be the frequency plus something that comes from the prediction distribution. Ignore this n, it's just to make sure that the things are, you're exploiting the underlying distribution as much as possible, but basically, if something is large on the prediction, I'm going to put larger bins into the flattening. So this is helpful for the parts that p hat is large and p is large, but it's not so helpful for the case that p hat is a small, but the actual pi is large. That's why we keep the sample setting. So the samples are taking care of these elements, and the prediction is taking care of the other type of elements. That the parts that they agree, p hat will take care of. The part that they disagree, the sample will take care of. But if your prediction is good enough, there are not so many elements of the second type. So what we could show is that if the distribution is indeed alpha close, the L2 norm that you obtain would be proportional to alpha over t. This second term is not important. This is theta, the minimum possible L2 norm. So if you just look at this first term, it says that you have a linear dependence to your distance between the prediction and the actual distribution. And this t is the number of samples that I needed to find out the frequencies. So alpha is helping me in a linear way to that number of samples. So now the algorithm is as follows. And you can see why this algorithm is resilient right away. I'm going to flatten the distribution the same way that I described. I'm going to estimate the L2 norm of the underlying distribution. Now, there are two possibilities. Either I'm successful, the L2 norm is lower than the number that I found in the lemma, or it's not. If it is not, it must be the case that the prediction was bad. Because a good prediction implies good flattening. If I find an evidence that it wasn't, I can just deny to solve the problem. But if the prediction was good, I'm going to proceed with the test. And now I'm going to proceed with the test that I showed earlier that was much more efficient when you have low L2 norm. So with this low L2 norm, I can run that test much, much faster. And as you can see, this is also resilient. That has resiliency property that I would never be bad, never be wrong, even when the prediction is wrong. So this is it. Thank you.
Any other questions? Yes.
I have a question, which is about the parameterization of the error alpha. So, I mean, it makes a lot of sense to interpret if alpha is a L1 distance. But is that like tight for your analysis, or is there some other like error parameter, like L2 distance or something else that?
It's a very good question. I wasn't like, I thought about the L2 distance thing. That's actually not very easy to show a similar density for L2 norm, but maybe we haven't spent enough time. Somehow for the analysis, L1 goes nicely. However, I can tell we don't need L1 closeness. What we need is the agreement on the large probability elements, which is much weaker than L1. Because in L1, even if you miss the probability of smaller elements, you would be sort of penalized for that, but that's sort of not necessary for our case.
Right.
So we have some experiments too, and in those experiments, you can see that you get much better results than the nominal alpha. And the reason is that large probability elements are actually easier to estimate. Like Chernoff-Found works nicely for large elements, so the agreement on the large element is actually much weaker than the agreement.
Thank you, speaker again.